closely at a modern silicon die. While software presents as an infinite, abstract space, every line of code you write is eventually bound to the physical geography and electrical limits of this metallic architecture. This infographic maps the specific machine levels that bridge the gap between human logic and digital physics. At the very top is Level 5, the application-oriented layer. Languages like C++ and Java exist here, designed specifically for human readability and high-level logic. However, the hardware cannot read these languages directly. Programs must compile downward, passing through Level 4 assembly language and the Level 3 operating system, which act as translation layers. Below those translation layers sits Level 2, the instruction set architecture. This is the exact boundary where software instructions meet the hardware in the form of conventional machine language. At the absolute bottom is Level 0, digital logic. This is the raw physical reality of transistors, memory banks, and system buses. To gain full control over how software performs, you must peel back these abstraction layers and understand the physical mechanisms waiting at Level 2. This photograph captures early computing. Before the 1940s, changing a program meant manually rewiring massive rooms of physical cables to alter the machine's logic. That changed in 1946. John von Neumann published a revolutionary design originally conceived by inventors John Mauchly and J. Presper Eckert for the EDVAC. Their solution was the stored program concept. Instead of wiring logic into the machine, both the data and the program instructions are stored together as uniform data inside the computer's memory. This diagram illustrates three distinct hardware systems: a CPU, main memory, and input-output. Notice the vertical arrows. Because all instructions and data share a single logical pathway to the CPU, a physical limitation emerges, the von Neumann bottleneck. The processor operates much faster than the memory can deliver data. This architectural bottleneck forces the machine to execute instructions sequentially, defining the rigid, mechanical nature of modern processing. So how do these three isolated hardware systems coordinate tasks across this bottleneck? They rely on the system bus. This is the shared communication superhighway that physically wires the processor to its memory and peripherals. It is split into three specific channels. The address bus acts as a locational guide. It carries specific coordinates strictly in one direction, from the CPU to the memory, pinpointing exactly where data is located. Once the location is found, the data bus takes over. It transports the actual payload, the binary instructions or WA values, back and forth between the components. Overseeing this traffic is the control bus. It carries specific electrical signals, like a read or write pulse, dictating exactly how the information transfer must take place. Software performance is ultimately limited by how efficiently data can traverse these specific physical bus pathways. This schematic maps the internal architecture of the central processing unit. When data arrives from the bus, these are the subcomponents waiting to receive it. The Arithmetic Logic Unit, or ALU, handles all mathematical execution and logical comparisons. The control unit acts as the primary orchestrator. It issues the commands that dictate what the ALU and memory do, and exactly when they do it. Surrounding them are the registers. These are ultra-fast memory locations built directly inside the CPU to hold data without the latency involved in accessing external main memory. The most critical of these is the program counter. This register holds the exact memory address of the next instruction waiting to be executed. The instruction register holds the current command being processed, and the accumulator provides a dedicated space to store the results of the ALU's math. The CPU contains no inherent intelligence. It is a highly organized physical sorting facility for routing binary data and triggering logic. Let's put this architecture into motion by tracing a single assembly command, add A, B, through one complete execution loop. This flowchart diagrams the instruction cycle. To process our command, the machine will repeat a three-step sequence: fetch, decode, and execute. The process begins with the fetch phase. Before the CPU can do any math, it must retrieve the instruction from main memory. First, the program counter uses the address bus to request the data located at memory address 100. Main memory locates that address and sends the binary instruction for add AB back via the data bus. The instruction arrives inside the CPU and is securely stored in the instruction register. Then, the program counter instantly increments its value to 101, queuing up the address for the next cycle. During this fetch phase, no math has happened. The CPU is operating purely on logistics, collecting the command to prepare for processing. Now the cycle transitions to the decode phase. The control unit analyzes the raw instructions sitting in the instruction register. It translates the add command into specific electrical signals, preparing the hardware components for action. The control unit identifies the values of A and B and routes them out of their registers and directly into the ALU. With the data in place, the system enters the execute phase. The ALU performs the physical arithmetic operation on the two values. The resulting sum is immediately stored in the accumulator register. If that result must be saved back into main memory, the processor initiates a memory write cycle. First, the processor places the target destination address onto the address bus. Second, it asserts a memory write signal over the control bus to prepare the memory for incoming data. Third, the processor pushes the sum out of the accumulator and onto the data bus. Finally, the processor waits for the memory to confirm storage, then drops the write signal. Every mathematical operation in computing requires this heavy, sequential traffic back and forth across the von Neumann bottleneck. Governing this entire three-phase loop is the system clock. It acts as a rigid, rhythmic metronome for the processor. Each micro-operation we traced, from placing an address on a bus to pulsing a write signal, is divided into strict clock cycles to keep the entire system synchronized. We traced one instruction slowly, but a modern clock dictates that this cycle fires billions of times every second. When this mechanical loop runs across millions of microscopic logic gates at these speeds, it generates an illusion. High-level application software, from web browsers to video games, is constructed entirely from this illusion of speed. Understanding these physical constraints, the system bus, the CPU registers, and the clock, allows a developer to predict exactly how their code will behave when it finally leaves the abstraction of the compiler.